The flux passing through a point charge when you are placing some disk at a distance from that, right? That means with the help of this solid angle, we derived an expression for the flux passing through the base of the cone when the charge is placed at the apex. So we derived one formula like q by 2 epsilon naught into 1 minus cos theta, where theta is the semi-vortex angle of that cone. Right, based on that we solved some problems. When a point charge is placed at a distance, some say x from the disk on the axis, then we can calculate the flux passing through the disk, like by forming a cone, right? And we solve it. The cylindrical example also I explained in the last class, right? Now one more problem is there based on that. Let us see this problem now. So see this problem now. Two charges plus q1 and minus q1 are placed at A and B respectively. A line of force emanating from the q1 at an angle alpha with the line AB, and then it at what angle will it terminate at minus q2. We know when two point charges like one positive and other negative charges are placed there, then lines of force, electric field lines will start from the positive charge and they end on the negative charge, right? So here they are giving the information like a line starting from the q1 at an angle alpha with the line AB. Then at what angle it will terminate at the angle q2 we need to calculate here. So for that we use that previous yesterday class concept here. So let us see how to use that one. So there is a given diagram here. A charge plus positive charge is placed at A and the negative charge is there at B. So this is a given information here. So a charge is a line of electric field line is starting from q1 at an angle alpha and it is ending at the terminating at the q2 at an angle beta, right? And so in this, now here many lines will be there. Not only this single line, many such lines will be there. So this is one of the line they are giving. So if a line is starting at an angle alpha, at what angle it will terminate at this charge q2 they are asking. So that is a question here. Many lines will be there. As we know, many lines will start from this q1 and many lines will end on this q2 here. So one of the line, if a line is starting at an angle, at what angle it will end at the charge q2 they are asking. So for that what I am taking is I am forming a cone here like as shown here. That means this I am taking this q1 here at the vertex and I am forming a cone here, right? And with the alpha as a semi-vortex angle. Now if alpha is taken as a semi-vortex angle, then number of lines of number of field lines passing through the base of the cone we can write by using our yesterday formula. So that is nothing but here I mentioned here the flux due to the charge q1 we can write as phi1 is equal to, this is our formula here, q1 by 2 epsilon naught into 1 minus cos alpha. Here alpha is a semi-vortex angle. And similarly, if you are taking this beta, this line is ending at an angle beta. Now the number of field lines ending at the charge q2 we can write as the same, the flux ending at this point here. That means we can consider the reverse case. That means the flux is entering through the base here and that is reaching this vertex here. And so that flux we can write as q2 by 2 epsilon naught into 1 minus cos beta we can write here. That is the flux due to this q2 passing through this base of the cone here with the semi-vortex angle beta, right? And so now here if this line is starting from this alpha at an angle alpha and it is reaching at a beta. Now the many lines will be there here. There may be many lines starting from this point here. And so now whatever the lines, those are starting at an angle less than alpha, then definitely you can say that all those lines will reach this point B here with an angle less than beta they will reach here, right? And so what we can write is whatever the line it is lying in this range, that means this flux must be equal to this flux. Whatever the line starting from this, all the lines should reach this point B here less than this alpha. There may be some lines which does not reach the point B. That means there may be, we know there may be some lines like this. So these are some electric field lines which does not reach this point B here. There may be such a lines may be there, right? But here what we are concluding is if line B, this line is at an angle alpha is reaching the point B, all the lines with an angle less than alpha with the line AB, definitely those field lines will reach the point B. Got it? And so this flux must be phi1 must be equal to phi2. All the lines less than this phi alpha here must be equal to all the lines reaching this q2 at an angle less than this beta. So that we can write as a phi2. So phi1 and phi2 are equal. So just we are equating that phi1 and phi2 here, and then this 1 minus cos alpha we can write as 2 sin square alpha by 2, and 1 minus cos beta we can write as 2 sin square beta by 2. And just here simplify this, we need the beta value. So sin beta beta by 2 is equal to, I am writing here. So finally beta is equal to 2 sin inverse of under root q2 by q1 sin alpha, that means sin alpha by 2 we need to write here. And you should remember here this q2, that means the q2 only magnitude of this charge we need to substitute here, not the sign. Only we need to substitute the magnitude of this charge here. So that is a flux, that means that is the angle at which this line will reach the or terminate at the charge q2 here. It is an important problem. So then just we are writing the flux by using this cone formula, and then we are equating the flux here. That's it. So up to this is one model of questions basing on this Coulomb's law here. Like from the beginning of this, Gauss law. From the beginning of Gauss law, we are discussing some problems like flux calculations. When some amount of charge is present are enclosed by a certain surface, then we are calculating the flux passing through that surface, right? Whether it may be line of charge may be there, or some charge may be enclosed there. And so regarding such a problems we are discussing there, right? And some other model will be there. And here one question will be there, like a theoretical question. Like if suppose this is a spherical surface, and within this spherical, suppose I am placing a dipole here. This is a minus q and plus q. If a dipole is placed within this spherical surface, then what is the flux passing through this spherical surface? So that means for this, just we need to write this q net or q in. That net charge is nothing but 0 here. If you are taking this as a Gaussian surface, the net charge passing through this will be 0. Net charge passing through this will be, that means net charge enclosed by this will be 0. Net charge enclosed by this is 0 means then you can conclude that flux passing is also 0. That means whenever a Gaussian surface is, that means a dipole is enclosed within a Gaussian surface, the net flux passing through the Gaussian surface will be 0 because net charge is equal to 0. So those are some problems based on this. When charge is given and the charge is enclosed within the Gaussian surface, then flux associated with the Gaussian surface calculations. Now there are certain other models will be there. The other model in the sense, there will be, that means they will give the electric field, and when electric field is given, then we need to calculate the charge enclosed by the Gaussian surface. How much charge is present in the Gaussian surface, we need to calculate there. And so let us see one of such an example here. And so see this problem now. A cube of side L has a one corner at the origin of the coordinate system extended along the positive x, y and z axis. Suppose that electric field in this region is given by E bar is equal to A I cap plus like see A plus B by J cap. Determine the charges inside the cube. That means here electric field is given here. When electric field is given, here you can observe this electric field is only along this z axis, only along the y axis, and which is a variable, which is a function of this y is given here. Now we need to calculate charge enclosed by this Gaussian surface here. Now let us see how to solve this. So that means just we need to calculate the flux passing, net flux passing through this total cube we need to calculate there, and after calculating the net flux we can apply our Gauss law. The net flux is equal to q by epsilon naught we can write, and from that we can calculate the charge enclosed by this Gaussian surface. Now this is the cube what we are assuming, or what is given in the data there, a cube of side L and one corner is at the origin, and this is our x axis and this is the y axis and this is z axis, right? And now this, first to see the phases what we are considering here. First I am taking this A, D, H, E, that means this phase I am taking here, which is parallel to this YZ plane. And so now for this plane we know electric field will be along this direction. That means I can say it is parallel to the surface, right? Because it is y axis is like this. So this electric field is parallel to the surface. And so now area vector will be along this x axis. So here you can observe that on this plane or on this face, electric field is parallel to the face and area vector will be perpendicular to the face. And so we can conclude that flux passing through the surface will be equal to 0, right? So flux passing through this ADHE surface will be 0. And next BCGF. So BCGF means next here So BCGF. So this is the phase here. BCGF. So on this BCGF, now we can write this the same thing. The only difference is electric field is again parallel here. The electric field will be parallel to this surface for this phase also. And area vector will be simply opposite to this. Opposite to this means here area vector will be along this negative x direction you will get, right? Because for this phase it is positive x direction, and for the opposite phase it will be along negative x direction you will get. And so there also field is parallel to the plane and area vector is perpendicular to the plane. So flux passing through that surface is also 0. So this is the second surface here. So first we discussed this one, next to this one, and next to see this one, CDHZ. So then CDHZ means this surface, CDHZ. So that means this base of this sphere here. Base of the sphere is nothing but we can write it as so base of the sphere is nothing but again this area vector of this base will be in downward direction, say negative z direction. And again electric field will be along this direction, parallel to the surface. So electric field is parallel to the surface and area vector is perpendicular to the surface. So flux passing through this base is also 0. And similarly flux passing through the top surface is also 0. Electric field is parallel to the plane and area vector is perpendicular to that. So electric flux passing through that that means electric flux passing through these 4 surfaces will be 0 here, or 4 phases will be 0. Next we need to calculate flux passing through the remaining 2 phases. So one is this one EFGH, that means which is lying in XZ plane. So if you want to calculate flux passing through that phase, that is that plane is lying in the XZ plane, that phase is lying in XZ plane. And so XZ plane means you can write y is equal to 0. Therefore, you can write the flux equation like this. So this is a flux through this EFGH phase. So then integral of E bar dA bar. Now our E bar is nothing but we can observe that E bar is given by this equation here. A plus by j cap. And so now here for that phase which is lying in the XZ plane, this y is equal to 0. So that you will get electric field as A j cap. Only this j cap component will be there. And so that means which is a constant value. So A j cap dot area vector is, as we discussed, area vector will be parallel to this, that means along the negative y axis. So we can write as L square into minus j cap. So finally we will get that flux as minus L A L square, right? And so next let us say this flux through this this phase here, A B C D. And so for this place you can for this phase you can consider that the electric field and area vector both will be in parallel direction only, right? And for this plane, this y is equal to, you can write it as L, which is a constant value. For any point here, that means this plane is again parallel to this y xz. So y is equal to constant here. So that is nothing but L. So then I can write this electric field as A plus BL j cap, which is a constant value now this dot L square j cap. It is along the area vector is along positive y axis. So again you will get this flux here. Now the net flux we need to write here. The net flux is nothing but flux phi1 plus phi2 we need to write. When you are adding these two terms, this plus A L square and minus A L square will be cancelled. So net flux is equal to B by L, BL cube you will get. And just we are writing the Gauss law here. From Gauss law we can write as this net flux is equal to charge enclosure by epsilon naught we can write. And so the charge enclosure we can write it as from this epsilon naught into phi, which is nothing but epsilon naught into BL cube. So that is the flux enclosure by the surface. So that is a way of calculating this charge enclosure by the surface here. So whenever this electric field is known to us, so we calculate the flux passing through the surface, and after calculating the net flux we need to calculate there. So that net flux must be equal to Q by epsilon naught. So from that we can calculate the charge enclosure by the surface, we can calculate there, right? So that is another type of problems in this Gauss law, based on this Gauss law. So let us see one more example based on this. So see this question now. In electric field in a cubical volume is E bar is equal to E naught into 1 plus Z by A I cap plus E naught into Z by A j cap. The edges of the cube are measured D and one of the corner lies at the origin of the coordinate system. Determine the net charge within the cube. So such a similar model here. So then you can write this as, that means this cube is again one of the corner is at this origin. So then we can consider this as again we need to take that means here now the difference between the previous problem and this problem is, previous problem is electric field is only along one direction like j cap, but here it is having the two components, I component, x component is there and y component is also there. And important thing is this x and y components varies with the z value. So that is the important thing here. So now let us see how to solve this. That means now here as the z is variable here, I am taking an element here at a distance of z from the base here. I am taking one such an element here of width dz, right? So then this is our element here. You will get like a thick plate, and the thickness of that plate is dz, which is very small here. That means a square. Just it is a square plane of thickness. The thickness of that plane is, we can say, dz. That is the thickness of the plane. So that means now for this will be one face for this plane, and this will be another face, and this is third, and this is the fourth here. Four faces we are considering here. Now for that small element, we need to write the flux passing through this each phase. And so now here if I consider this first phase here, this is our first phase here. So now for this phase, electric field perpendicular to that surface will be x component of field will be there, because y component if I consider tangential, due to that y component no flux will passes through this first phase, right? That means number one, phase number one. And so now electric field flux will be there due to this x component, which is E naught into 1 plus z by a I cap, right? Now area of this space will be along this direction. That means that is along x direction. And so just this flux means we need to multiply these two values here, right? And so which is a positive value. Now that flux is positive because dA and E bar are in the same direction. Now for the opposite phase if I consider, that means for the phase 3 if I consider here. Now for the phase 3, electric field will be along this direction and dA value will be along this direction here. So they are opposite each other. And electric field will be same component will be there here, because z is same for this space and this space also. And so same amount of electric field will be there, but area vector will be opposite. And so simply I can say that flux will be here, same amount will be there, but it is negative. I mean simply here through the phase 1, through the phase 3 the flux is entering, and the same amount of flux is passing through the phase 1. And so that the resultant of net flux passing through this 1 and 3 will be equal to 0. That we can conclude here. Now similarly, if I consider 2 and 4. So if I consider this 2 and 4, the flux passing through the 2 will be only because of this y component, because x component will be parallel to the plane, and so flux passing through that due to that x component will be 0, right? And so only due to this y component this flux will be there. And now dA for this phase 2, the dA will also be in the same direction. So here again the flux passing through this phase 2 will be a positive value, which is the product of dA into this y component. Now similarly for this 4 if I consider, this electric field vector will be like this, and that means electric field vector will be along positive y-axis and area vector will be negative y-axis. So they are opposite each other. So that means again the field strength will be same, because z is same here. And so same flux you will get, but with the negative sign. So right, again if that means here again also we can conclude that whatever the flux entering the phase 4, same flux is leaving the phase 2 from this side. So right, and so that the net flux passing through the 2 and 4 will be 0, right? And so now the net flux passing through the entire this element will be 0, because 1 and 3 will cancel with each other and 2 and 4 will cancel with each other. So through that element net flux will be 0. And so that like you may consider such a number of planes are placed one above the other, so that this total cube is forming there. And so now the net flux through that entire cube will be 0. And so that we can conclude that the charge enclosed by the surface will be 0, right? Charge enclosed is also 0 here. So that is that question. Now similarly, so let us solve this question here. So solve this question. An electric field in the given region is given by E bar is equal to E naught x by L I cap. Find the charge contained inside the cube of volume bounded by the surface x is equal to 0 to x is equal to 0, x is equal to L, comma y is equal to 0, y is equal to L. There's a cube like this, and z is equal to L. And this z axis will be positive axis will be that side only, or you can take QBs like this, like previous problem. So you will get the answer like this. This E naught into, that means epsilon naught into E into L square. So try this problem and final answer, check with this final answer here, right? And let us take another such a problem here. In a region of space, electric field electric field is given by E naught into xi cap plus E naught into yj cap. Consider an imaginary cube of volume of edge A with edges parallel to the axis of the coordinates now. That means now it's a multi-correct answer type question. Like you need to answer this flux regarding this flux calculations here. Flux passing through the 1, 2 like this. They are asking 2, 1 and 3 and 2 and 4. So like that you need to calculate flux passing through each flux. So for this the answer will be AB. So check with that answer, right? And so now let us take this another question. This is an important question here. So a similar problem, but the surface will be like a spherical. Now that means previously we discussed almost all the problems will be in the form of like a cube. Now these are spherical surfaces. Now see this. The intensity of electric field depends on the coordinates x comma y as shown as follows. E bar is equal to ax I cap plus ax I cap plus yj cap by x square plus y square, where a is a constant and I cap and j cap are the unit vectors of the x and y axis. Find the charge within the sphere of radius r with the center at the origin. So that means now the electric field depends on this x and y coordinates here. Now with the they are asking the charge enclosed by the sphere. They are asking the sphere of radius r. Now suppose take here we are taking a small element, and so now the small element n cap, that means the area vector we are taking like this. The direction of area vector like I cap, that means like xi cap plus yj cap plus zk cap we are taking. That's like a unit vector we are taking there. So then x by root of x square plus r square plus x square plus y square plus z square. So that we need to divide that position vector with that, right? So that gives us unit vector. And so as the radius of the sphere is given as r, and so then we can write this as this term, the like root of x square plus y square plus z square, you can write as r. So then we are writing like this. So that means finally that unit vector n cap we are writing as x by r I cap plus y by r j cap plus z by r k cap. Now the flux passing through the small elemental area we are writing here, right? So then d phi is equal to we can write this as so d phi is equal to, we can write this as E bar, that means E bar whatever the expression is given here, that E bar we are substituting here, E bar dot n cap into dA. dA is now the magnitude of that area of this element here, right? So now if you do the dot product of this E bar and n cap, then you will get this vector here, ax square by r into x square plus y square plus ay square by r plus r into x square plus y square. Now we can add these two terms. That means we can take a by r common, then x square plus y square by x square plus y square you will get. The term will be cancelled, right? And so now the this dA is independent of the coordinates what we are getting here. Now this is the d phi, flux passing to the small element here, and so that will be the independent of x and y. That means now this in this d phi term there is no x and y terms here. And so just we are integrating the term here. That means a by r is a constant that we are writing outside. Integral of this dA, integral of our ds, that means dA or ds area. So that we are writing as a by r into that integral of ds. dA is nothing but our area vector here. We are taking it as a here. So let us write this as dA, integral of dA. And so then integral of dA is nothing but total surface area 4 pi r square you will get. So epsilon naught pi a r you will get, and that should be equated to our, according to our Gauss law, that should be equated to this q enclosed by epsilon naught. And so from this we are getting this q enclosed here 4 pi epsilon naught into ar, right? So that is the charge enclosed here. So that is a way of solving that charge enclosure problems here. We need to calculate just flux passing through the total given object, and that net flux we need to calculate there, and that net flux should be equated to this q by epsilon naught, our Gauss law statement. So from that you can calculate the q value by just by cross multiplication that. And then now let us see this another concept is there here, the differential form of this Gauss law. It's an important, and generally this will be required for this advanced type questions. And so then differential form of this Gauss law means we are expressing this Gauss law like our previous form is nothing but we call that as integral form. Integral form is nothing but what we are writing here, like the flux will be equal to integral of this, actually we call it as surface integral, E bar dot ds bar or dA bar is equal to 1 by epsilon naught times the charge enclosed, right? So this is our Gauss law what we are writing, or the statement or the mathematical form of the Gauss law here, right? And so now this form is actually we call that as different integral form, because here integration is there here. Now we are going to express that in differential form here. And so differential form is then just this we call surface integration. So that surface integration will be converted into this volume integration by using this equation, this term. That means integral of this is nothing but integral of E bar dot ds bar is equal to integral of del bar dot E bar into dv. So this we called actually volume integration. This is a surface integration. Surface integration, that means in integration 3 types will be there: line integration, surface integration, and volume integration. You will get in mathematics. I think in intermediate level it is not there. I think it will be there in engineering. And so now in this 3 types of integration: line integration, aerial surface integration, or the volume integration. So in Gauss law what we are writing is surface integration, because you know Gauss law is we apply the Gauss law over a surface. That means in order to apply the Gauss law, first we need to choose a Gaussian surface that we already discussed there. So right, that is a surface integration. Now we are converting the surface integration into volume integration here. And actually that by using this Gauss divergence theorem, this relation is called this is surface integration is converted into this volume integration. So there the del the term del is nothing but we call it as del, which is an inverted triangle, like this. We need to represent like this. And this we discussed already at the conservative or non-conservative force in mechanics. At the conservative or non-conservative, while verifying whether the given force is conservative or non-conservative, we use this operator there that we call del operator. And so now actually this thing is not required here. Just you need to remember here that conversion here only for this point it will be useful there. And now this just we are replacing in this Gauss law equation. This is our original Gauss law equation. So in this we are replacing this surface integral of E bar dot dl bar with this volume integration. The same thing in volume integration we need to write like this: integral of del bar dot E bar. This is in vector form only, del bar dot E bar. This is a dot product actually. So I will write in vector form so that you will get the clarity about this. So this is the E bar. So del itself is a vector operator only, that is. So del bar dot E bar into dv. So dv is a small elemental area, right? And so now we are writing this. That means this term we are replacing with this, and this charge enclosed we can write as this charge enclosed by this object dq we can write as for the volume distribution. We can write generally as rho into dv, right? And so the total charge we can write as integral of rho into dv. Right? So this is the charge enclosure here. So that we are writing in this equation here. You can observe this. This term we are replacing as like our so this term integral of d bar E bar dot ds bar, we are replacing it with this integral of del bar dot E bar, del dot E bar into dv. dv is a small volume element, and into 1 by epsilon naught times the q we need to write here. So this q we are expressing like this. And just we are writing this term this side, and so then you can cancel this integration and dv term, and so now we can write this as del bar dot that means del dot E bar is equal to this rho by epsilon naught we can write here. So finally we will express like this. So that means here finally we need to write this differential format. This is our del bar dot E bar is equal to rho by epsilon naught. So this is our equation here. This is a Gauss law in differential form, right? So now some of the student I think may don't know about this del operator. It is simply nothing but we can write this del operator as, so where del operator I can write this as so given by this. So I cap of, that means dou by dou x plus dou by dou y j cap plus dou by dou z k cap. So this is our del operator meaning here. So I, and that means dou by dou x I cap plus dou by dou by j cap plus dou by dou z k cap. That means it's a partial differentiation, you know. That is the meaning of this del operator here. Got it? And so now here that means actually this is the differential form, and this total derivation is not required for you. No need of remembering this total derivation, and Gauss divergence theorem is also not required for you. Just remember this as a differential form of this Gauss law here, this equation. So finally you need to remember this equation as a differential form of this Gauss law here, right? And so actually this is nothing but simply in a normal language, if you want to explain, then simply I can explain like this. This is a general procedure for explaining this. In a normal language, simply if I want to explain this, just both sides divide with the volume here. So here this is our equation here. Both sides we need to divide with the volume. So charge per unit volume will give us this charge per unit volume is nothing but charge density. So this side you will get rho here. And so, but whereas this side you will get this, this is area of this element, and then that means what actually I am saying is integral of, so actually should not write like this, just I am trying to explain how to get it dimensionally. So that means what I am doing is this value, let it be dq only, or integral of dq let us take here, then this we are taking as dv, then this is, we are dividing with this dv both sides here. Then integral of dq by dv is nothing but that gives the average charge density, which we can write it as rho. And this side, see here, this is the this term is nothing but our surface area, and this is the volume. So surface area by volume is almost you will get some distance, one dimension you will get here. That means distance measurement you will get here dimensionally. So that is nothing but what we are getting here. That means here you will get like suppose only the field is having the x component of electric field is there. Then simply what I can express it as like dou E by dou x I can write here. For example, if by substituting this operator here, this is a dot product here. You should remember this is our differential form is del bar dot E bar is equal to rho by epsilon naught. Now what I am saying is if the electric field is having only x component like A naught into some E naught into x is there, then this expression we can write as dou E by dou x is equal to rho by epsilon naught we can write here. So that is nothing but electric field per distance you will get. So that is nothing but what we are getting here. So that means you can simply understand like this. This form is nothing but similar to just we are dividing both sides with the volume. So then you will get a form like this. So this is a differential form here. And there is some importance for the differential form. There will be some problems based on this differential form here, right? So remember this is the differential form. Del dot E bar is equal to rho by epsilon naught, where del is given by the operator del is given by this expression dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap, right? And now let us see this some applications based on this. And so now see this problem. The field potential in a certain region of space depends on the x coordinate as phi is equal to minus ax cube plus b, where a and b are the constants. Find the distribution of space charge. That means rho of x we need to calculate here. Got it? So here they are giving the potential. This is nothing but actually potential. So that means in foreign books they will represent that potential with this symbol phi here. That previously phi we are using for this flux. Don't confuse with that symbols. Those are not the standard symbols. That means these are this is not the flux here. Remember, got this? This is the electric potential. So what they are giving here, electric potential. So I am taking that as a V only, right? So that there is no confusion for you. So then V is equal to this potential is equal to minus ax cube plus b. So this is a potential given there. Now from this they are asking that charge distribution. So for this charge distribution, that means we need to use now this our Gauss line differential form. If you use the Gauss line differential form, you can calculate that easily. So then this is nothing but del bar dot E bar is equal to 1 by or rho by epsilon naught we can write here, right? And so now from this first we need to calculate the E value. And so it is given that this electric field only depends on this x component, x coordinate here. So we know this, if potential is known to us, then we can calculate the field minus dV by dx, because it is only x component is there. So I am directly writing it as dV by dx. Otherwise you need to remember that The EV relation is also in terms of differential, that means partial differentiation only, like minus dou by dou z dou x of I cap, or minus of, I am taking minus common, then plus dou by dou y of j cap plus dou by dou z of k cap. In EV relation we already discussed that, right? And so now here it is only x component only, so that I am taking this only dv by dx I am taking here. So therefore minus of, if we differentiate this, so minus 3a x square you will get. And so therefore this electric field will be, I can write this as then minus of minus plus you will get 3a x square you will get, right? And so now here what I can say here is this is the electric field value. And so now we need to write this, I can write this as it is having only x component here, right? X component means, suppose in vector form I can write this as I cap. Just adding the direction here, so that this is our E bar here. Then what I can write is, so then to get this vector form, here itself we can take the partial differentiation. Then you will get this automatically, this vector form here. Like what I am saying is, you can take this E bar is equal to minus of like dou v by dou x I cap plus dou v by dou y j cap plus dou v by dou z k cap. You can take directly in this form, then automatically you will get the direction of this field also, right? And so now let us see, we need to substitute in this differential form here. Now in this equation we are going to substitute that equation now. Now I am writing the del bar, see this carefully. Now I am writing the del bar. That means I am writing this value of del dot E bar. So this value I am going to write here. So as I said, this del is nothing but dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap, right? So this is our del dot. Now E bar we need to write. Our E bar is nothing but 3a x square I cap is equal to, our Gauss law is rho by epsilon naught, where rho is a volume charge density. Got it? Now just to do the dot product here. So if you do the dot product and differentiation of this, so 3a I can write outside. So 3a into dou by dou x of x square we can write here. So then remaining terms will be 0 you will get. So this will be equal to rho by epsilon naught. And so from this I can write this rho is equal to, you can simplify this. This will be 6a epsilon naught into x you will get. So this will be the charge density here. So the volume charge density is also varying with the x. So that is given like this. So that is a way of calculating this charge density if this potential is given for us. That means especially in this charge density calculations, if you are using this Gauss law in differential form, you can calculate that more easily here. This question is nothing but from this Irido book. So from the font itself we can observe this. So then this is the application of this differential Gauss law in differential form here. Got it? So again see here del operator. This del operator is nothing but, that means this instead of del, when we are substituting the when you are doing the calculation, this del value we need to replace with this dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap dot whatever the E function is given. Here only x component is there. If it is having other components also, whatever the expression for E is given, so that expression we need to substitute here. Then after that dot product, then any differentiation is required, then we do the differentiation, we carry out this differentiation. So that should be equal to rho by epsilon naught. From this you can calculate this rho value here. So next let us see one more example based on this, then you will get the more clarity about this. And so now see this question here. And now here this question is, the electric field inside a charged ball depends only on this distance from the center as phi is equal to a r square plus b, where a and b are the constants. Find the space charge distribution inside the ball. So similar question, but the function is some different function is given here. A r square, where r is the radius of this ball here. And now here I am taking this. So if r has a radius of a, that means if you are taking it as a radius of a particular sphere, then we can write this as that r square I am taking it as r square is equal to, like, on the surface of that particular sphere I am taking x, y, z are the coordinates. Then we know we can write that r square as x square plus y square plus z square. So that I am converting this formula in terms of x square plus y square plus z square, so that you can apply our differential form easily there without any confusion. So now see this. Now this expression I can write as, again I am here, this phi is given for this potential, again this again potential, you can read this. So now I am replacing with that phi as v, our usual symbol I am writing here. And so now this is ax square or a of x square plus y square plus z square plus b. Got it? I am just replacing this r value with this x square plus y square plus z square by taking that x comma y comma z as a point on the surface of the sphere. Next, same process. As the potential is given, we need to calculate the field, and after calculating that field, we need to apply this Gauss Law in differential form here. So from this I am going to calculate this field, and so that field I can write as E bar is equal to minus of so dou v by dou x I cap plus dou v by dou y j cap and plus dou v by dou z k cap. So then just simplify this differentiation here. So then I can write this as minus so here x square differentiation is 2ax plus similarly 2by, sorry, a, that is also a only. So then I can write this as 2ay and plus 2ax I cap. This is components we need to write here. This is j cap and 2az k cap, and differentiation of this b will be 0. Or otherwise I can express this field as, I am taking that minus 2a common here, that means 2a common here. Then this can be expressed as xi cap plus yj cap plus zk cap, right? Now let us write this Gauss Law in differential form here. Now our Gauss Law is nothing but del dot E bar is equal to rho by epsilon naught, right? Now let us substitute this, our del operator. Now del is nothing but, say this, dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. Got it? This is our del operator. This is k cap dot. Now E bar we need to write here. So that E bar is nothing but minus 2a into xi cap plus yj cap plus zk cap. This value should be equal to rho by epsilon naught, right? Now let us simplify this equation now. So this part is different. So now let us simplify this equation now. So this step I am simplifying here. If you do the dot product first here, then minus 2a I am writing outside. So minus 2a. Then dot product is nothing but x. So then x differentiation is 1. So then 1 plus, similarly here dou y by dou y you will get, right? If you do the dot product of this j component. So that's the differentiation is also 1. Plus similarly z component. Here differentiation of z with respect to z is 1. So that is also 1. So this is equal to rho by epsilon naught. And so now here 1 plus 1 plus 1, that is 3. 3 into minus 2a. So minus 6a you will get. And so from this I can write this rho is equal to minus 6a epsilon naught. So this is the charge enclosed by this sphere here, right? So now here it is a negative charge distribution here. So then here we are getting the positive charge and it is a variable. Now here we are getting it as a constant value here. So that is a way of calculating this charge distributions here, right? That is a way of calculating this charge density. So that means in the previous calculations we solved flux, finding the flux. If charge distribution is given, when charge is enclosed by some object, we calculated the flux, right? And in today's class, when electric field is given, then how to find the charge enclosed by the surface. So that such a type of problems we solved. And then next we discussed about differential form of the Gauss law and then how to apply the differential form of this Gauss law here. And as I said, don't confuse with the derivation of the differential form of the Gauss law. It is not required to you. And just remember this differential form of this Gauss law formula here. Just if you remember this formula, that's sufficient here. The general equation what we are writing as that we call integral form, and this we call the differential form. And this differential form is especially used for this type of problems here. When they are giving some potentials and when they are asking like find the charge enclosed by the surfaces, and especially for such a type of problems we need to use that differential form here. Then we can calculate the charge densities here. And especially you can simply remember it as whenever charge density, directly when they are asking the charge density, then it will be related with this differential form here. We need to use this differential form here, right? In the next class, we will discuss some derivations based on this Gauss law. That means these are some problems based on this Gauss law here. So based on Gauss law, lot of applications will be there, right? So up to now we discussed some simple problems based on this Gauss law here. Either flux calculation, finding the flux, or finding the charge, or finding the charge density like this. And so now there will be some other applications of the Gauss law will be there. Like whatever the field derivations, electric field due to the line of charge, electric field due to this plane of charge, whatever the derivations we did in the first topic, that means in the from the Coulomb's law electric field derivations we derived some expressions there. Now those derivations we can also do simply by using this Coulomb by using this Gauss law here. So we can do those derivations. That means we can find the electric field due to the symmetrical charge distribution very easily with the help of this Gauss law. So in the next class I will explain those Gauss law calculations, that means derivations based on the Gauss law, and after that again some problems and the other applications will be there. So this, as I said from the beginning of Gauss law itself, this Gauss law is very important topic in electrostatics, because whatever we derived previously, those problems, majority of the problems we can also solve with the help of this Gauss law here. More easily we can solve actually with the help of this Gauss law. And we can solve some problems only with the help of this Gauss law. Otherwise the calculations will be very lengthy, calculations will be there, right? So Gauss law is very important. Don't neglect this part here. You have to practice many problems based on this Gauss law here. As you know, in Singh's that separate topic is there for this Gauss law here. So go through the solid examples and the conceptual applications and all the problems based on this Gauss law here in that topic, right? So in the next class I will explain those derivations based on this Gauss law, electric field derivations in the sense. So thank you.